Okay guys, so I'm going to discuss correlations. I'm going to discuss the different types of correlations, raw correlations, partial correlations and part or semi-partial correlations. I'm going to describe how they're calculated. Now you don't need to remember this. This is just to help you understand how to interpret the different types of correlations, why we use the different types of correlations. Yeah. That's it basically. So you can see here I have a Venn diagram. This is the DV, the blue circle. This is IV1, the yellow circle. And this is IV2, the pink circle. I've got a few different calculations here for how to calculate the different correlations for the different variables. So I'll just start with the raw correlation. So you can see the raw correlation equals the unique variance, or sorry, not the unique variance, the shared variance between an IV and a DV. So for IV1 and DV, the raw correlation is D plus F over the entire variance in the DV. So D plus F over D plus C plus F plus G, which you can see here, D plus F plus D over D plus C plus F plus G is the raw correlation. So it's the correlation between the IV and the DV, ignoring any other variables that might be entered into the regression. So for IV2, it's F plus G over D plus C plus F plus G. Okay? So just to give you an example, this is a correlation table taken from your textbook. So if you wanted to interpret the raw correlation of patient age in step 1, you guys should be really familiar with this from previous years. You just say, there is a weak negative linear relationship between patient age and patient satisfaction with visit. So the raw correlation is here, negative 2.71, so it's negative and weak. So this is patient age, and the zero order is the raw correlation. So the partial correlation, we're only considering unique variance. So for IV1, it is D over D plus C. So it's basically a ratio of the unique shared variance over the remaining unique variance in the DV. Any variance that's shared with other variables is not in the equation. Okay? This means that you end up with a different denominator for each variable. So for the partial correlation for IV2 would be would be G over G plus C. So you end up with a different denominator. The denominator for the partial correlation for IV2 is G plus C. So this makes it difficult to compare the partial correlations. Okay. So I'll just give you an example. So here you can see the sentence that you would use is after controlling for, so it's the same as for the raw correlation, but you just start out by mentioning that you're controlling for other variables. So after controlling for IV2, there is a weak, moderate or strong, positive or negative linear relationship between IV1 and the DV. So here's an example going back to patient age. Your partial correlation is here, negative 2.06. So when we're going to start by saying we're controlling for the other variables. So when length of consultation and whether patient is seeing their usual doctor are statistically controlled, there is a very weak negative linear relationship between patient age and patient satisfaction with visit at step 1. So it's exactly the same as the raw, the phrasing is exactly the same as for the raw correlation, but you need to start by mentioning that you're statistically controlling for the other variables that have been entered in that step. Okay, so if it was step 2, you would say after controlling for length of consultation, whether patient's seen their usual doctor, doctor's perception of patient participation and patient's perception of participation, there was a very weak negative linear relationship between patient age and patient satisfaction with visit. Okay, you don't necessarily need to say at step 1 because it's obvious, but I'm including it today for demonstration purposes. So here the part correlation, on the other hand, is the unique variance between an IV and a DV over all of the variance in the DV. So for IV1 it will be D over D plus C plus F plus G. For IV2 it will be G over D plus C plus F plus G. So this means that the denominator is the same for all of the IV, so that means you can actually compare the different correlations for the different part correlations for different variables. And you actually square these variables and you come up with an effect size. So because you can compare them, you can use it as an effect size and see which variable explains the most variance in the DV. So I'll show you how to interpret it. So again, looking at patient age, you'd say something like, at step 1, patient age, first of all, sorry, I'll just quickly explain, you need to square this, so negative 0.196, so if you square that, you get 0.0384. You multiply that by 100 to get a percent, so it's 3.84%. So you would say at step 1, patient age accounts for an additional 3.84% of the variance in patient satisfaction with visit, which cannot be explained by the other variables at that step, which cannot be explained by length of consultation or whether the patient is seeing their usual doctor. Okay, so just make sure you don't say at step 1 patient age accounts for an additional 3.84% of the variance in patient satisfaction with visit, which cannot be explained by the other predictors. Make sure you actually spell it out. This is a technical document, so at step 1, patient age accounts for an additional 3.84% of variance in patient satisfaction with visit, which cannot be explained by length of consultation or whether the patient is seeing their usual doctor. Now, when you do a correlation, when you do table 2, the result of your regressions in the report, you always include the part correlations, so actually the squared part correlations, so the variance explained by each predictor, and you also always include the beta weights. So I'll talk about some reports in a later video. Okay.